Okay, we're going to go ahead and continue with question 4.11, 4.11. Here we go. So, a spring-loaded piston cylinder device initially contains 1 kilogram of water with 10% quality at 90 degrees Celsius. So already we know the state, right? Because by telling us there's some, non-zero or some quality between 0 and 1, it's telling us that it's a mixture. The value of that quality plus the temperature is giving us the actual state. So then we know the first state. Heat is now added to the medium until the temperature reaches 250 and the pressure to 800. Okay, so if that is a superheated vapor, then we do know the state is 250 and 800. So that's good. We know the initial and final states. We know the initial and final volumes. Calculate the total work resulted from this process in kilojoules. Okay, so we know the initial and final volumes, so we can calculate the work. But now the question is, how do we calculate the work? Because going from one state to the other state, the work depends on how you get from point A to point B, right? Or state 1 to state 2. And in this case, it's something a little different from what we've seen before the other questions. It's a spring-loaded piston cylinder device, right? So we have a piston cylinder, that's nothing special, but there is a spring here. So if we ever want to push or pull against the spring, we're gonna have to fight a little harder. And the reason this gets a little tricky is because in a traditional piston cylinder, the pressure inside is going to exactly equal sort of the pressure that would need to be there to support the weight of the piston, just the weight of the piston. But in this case, we now have to not only support the weight of the piston, we also have to fight against the spring. But the spring force itself is changing because we know from just physics, F equals negative kx. It's a function of the displacement of the piston. So if the force that we're fighting against is always changing, that means that our pressure is changing, which is different from what we're used to in this case, where we say, okay, well, the pressure is constant as long as there's no stops, right? Here, it's not the case because as we push, we have to build a bigger pressure to push harder and harder because it's going to get harder and harder because we're going to squish the spring more and more. So before we actually get into the math or solving the problem, I just want to go over how we can do this really. So we have, say, a graph of pressure and volume, right? And because we know that work is the integral of P dV, that's like saying the area under whatever curve is in this graph is going to be Vx. We know that's supposed to be an integral. It looks like a D, sorry. Basically what that is telling us, however we work this integral out, the point is that whatever is under this graph or this curve going from state 1 to 2 is the work done, okay? Is the work done. Now, because of spring, negative kx, it's a linear function. That means that the force is going to increase linearly as we move. The pressure is going to increase linearly as we move. So we know going from state 1 to 2 is linear. We also know, I'll just do a different color for a change, that the work done is represented by the area under this curve going from state 1 to 2 or 2 to 1, however you want to look at it, depending on the case, right? We know that the area or the work done is this green area here. And clearly we can see that this is a trapezoid. So that's pretty simple. So this is pressure 1. We draw sort of this is pressure 2. This is volume 2, and this is volume 1. So we know a trapezoid. If we look at this sort of sideways a little, maybe it's a little clearer. But the area of this trapezoid is big base plus little base times height divided by 2. So big base plus little base being this guy and this guy. So P2 plus P1 times the height, which is V2. So let's bracket that. V2 minus, these should all be strike throughs, V1, so big base plus little base times height divided by 2 is the work done. on the system. So we know we can find the initial and final pressures and the initial and final volumes from the information we have about the states, and then we can plug that in and solve for the work, which is what we're trying to do for this problem. So let's just keep this image in the back of our minds as we solve for the states, which we will do here. I'm just going to bring up the question again on my other screen. So yeah, we have 90 degrees Celsius, 10% quality. So let's see what that gives us. So because we have some quality, we know that it's a mixture. Go straight to the mixture tables, sorting by, way too far there. Sorting by temperature, we're told 90. So it's going to be on this line at 90% quality. And 90% quality means that the internal energy is 90% of the way between 10% quality. So that means that the internal energy at this state is 10% of the way between UF and UG. The enthalpy of this state is 10% of the way between HF and HD. The entropy of the state, which you'll learn about later, is 10% of the way between SF and SG. And what interests us, the specific volume, is 10% of the way between VF and VG. So let's find out what that is. So from the quality, let's just write it out, it'll be a bit clearer. 0.1, being the 10% quality, is equal to V, which whatever it is what we're trying to find, minus VF over VG minus VF. So all of these values except V1 are known. And if we work it out, we'll get that V1, the specific volume anyway, at state 1, is equal to 0.23686 meters cubed per kilogram. And if you don't know how we got this, I recommend you look back at the videos from chapter 2. All right, but this is the specific volume at state 1. All right, that's good. But of course, we want this in terms of volume, right? Because that's how the work equation is in terms of volume. So all we have to do is multiply this by the mass of the fluid or of the material inside. We have 1 kilogram of water, so that's pretty convenient. This means that the volume is equal to V1 times 1, so just 0.23686 meters cubed. This is the initial volume. All right, so these two are pretty important results. Now let's look, this is state 1. Let's look a little bit at state 2. So state 2, what are we told? We are told that we have a temperature of 250 and a pressure of 0.8, I believe. Let me just confirm. Sorry, just looking at the wrong thing there. If we go back to the question, okay, if we go back to the question, yes, we're going to 250 Celsius and 800 kilopascals. So we can go straight to these tables and figure out what that is. I'm guessing it's a superheated vapor, but I don't really know. But let's guess superheated vapor and see if that gives us something that makes sense. So 0.8, because 800 kilopascals is 0.8 megapascals. 0.8 and 250. So good, we do have an entry for that. We are on that line. So 0.2608, all right, is the specific volume, right? This is what that column is. 0.2608 is our next specific volume. Drop the pencil there. 0.2608 meters cubed per kilogram. And again, to get the actual volume, we just multiply it, in this case, by 1, because our mass is 1 kilogram. And we're going to get 0.2608 meters cubed. So actually, one last thing we forgot to do for state 1 is we need to know the pressure. We need to know the pressure at state 1. We know the pressure at state 2, it's given. We just found V1 and V2, that's given. Well, not given, but we found it. P1, though, we need to find. So if we go back to state 1, we saw the mixture at 90 degrees Celsius. Since it's a mixture, the pressure has to be the saturation pressure. So let's go back and check what that was. Here we are, 90. So 70.14 kilopascals right here is the saturation pressure. That is our initial pressure, 70.14 kilopascals. So P1 equals 70.14 kPa. All right, so now let's take this and this, and of course we were given that this was at a pressure of 800 kilopascals. And this, let's pop it into here and see what the work done is. Okay, so 70.14 plus 800, and these are all times 10 to the 3, so times 1,000, put it into pascals. Plus, times the difference in volume. So we went 0.2608, which is our final volume, minus the initial volume, which is 0.23686. Divide by 2, getting a work output of, or input in this case, 10,415.58 kilojoules. Sorry for the delay there. I realized I just made a small mistake. I misread the table. So you see, I circled on the wrong line. I want the one below, 0.2931. So just to note, V2 is this is wrong here. The pressure is given, so that's fine. But V2 is really 0.2931 because we only have 1 kilogram. We're just multiplying the specific volume by 1. Meters cubed. So it's this that you want to plug in, not this guy. This was read from the wrong line of the table. Anyways, if you do calculate this, your final answer in terms of the work done will be 24.52 kilojoules. This is the work done by the system. Okay, and it's positive, so that makes sense. We have an increase in volume. Okay, thank you.